The last video, Limits 1, had you look at limits graphically. As you know, we need to look at limits graphically, numerically, analytically, that's algebraically, and we also need to be able to write about limits. We're going to start out by looking at tables, which is the typical way to do numerically. So I'm going to have the table from the left of -5, from the right of -5. I've given you the appropriate y values. And so as I approach from the left, these are getting closer to -3, itty bitty steps. These are getting closer to -3, itty bitty steps. They both equal the same number. Therefore, we say we have a limit of -3. Our function value is -3. Notice both of these are equal, so when the limit equals the function value, then we're continuous. And actually, it's when the function value equals the limit that we're continuous, is the way that we're supposed to state it. Now, away from that and into our discontinuities. When I approach this table, it will be 4 from the left and 4 from the right. Appropriate y values from below, from above. Itty bitty steps, I get to 2. Itty bitty steps approaching 2. They're both the same, so the limit is 2. But note this function value is not defined. And so the limit cannot be the same as the function value, or the function value the same as the limit. It's not there. It's not equal. And so we call this a point discontinuity or a hole. Later on, we're going to tell you that we're able to call this one removable and remove it. Just keep that in mind. So now, when I look at this table, I'm approaching -3 from below and from above, from the left, from the right. I've given you the y values. Notice itty-bitty steps, and I'm getting to -4, itty-bitty steps, and it looks like it's getting to -4. These two are equal, so my limit is -4. But note my function value is 8, and 8 does not equal -4. The function value is not the limit. They're not equal. So again, we have a hole or a point discontinuity. This is, again, something that's going to be called removable later on. Now we're moving to another type of discontinuity. And so I'm looking at the number 1. I'm going to look from the left and from the right, from below, coming in from above. Note this one, itty-bitty steps to -1, itty-bitty steps to 3. They're not equal. So notice they're both real numbers, but they're not equal. And when they're both real numbers and not equal, of course, it's D and E because they're not equal, but that's also the definition of a jump. Unequal real numbers forms a jump. Notice the ordered pair doesn't matter. And when the limit doesn't exist, we're going to call this later on a non-removable discontinuity. So some more on jumps. Let's look at this one. I'm coming into -1 from below and from above, from the left, from the right. Here's the y values. Here's the ordered pair. Notice itty-bitty steps squeezing in on 1, itty-bitty steps squeezing in on -3. Two real numbers, but they're not equal. Not equal means D and E. Two real numbers, not equal means jump when the left side doesn't connect to the right. And yes, we have a function value that's rather useless. Again, it will be called not removable or non-removable. Let's do one more jump. So here's 0. I'm squeezing in from the left side and the right side. I've given you some values for y. Itty-bitty, 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 -2. Slowly, 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 2. These are two real numbers again. They're not equal, so D and E. But since they are real numbers and not equal, it's a jump. And I do have an ordered pair. Once again, doesn't help us much. Now let's move to the infinite vertical asymptote, unbounded. Now, how do we tell these? Let me get the sunlight out of there. So I'm still going to squeeze in. So these are doing itty-bitty steps, but look over here on the y side. The y guys, the y values are growing smaller and smaller and smaller. I guess they should say they're shrinking, heading towards Satan. Negative a million, negative a billion, negative a trillion, 10, 100, 1,000, million, trillion. Notice leaps and bounds, not itty-bitty steps. So when you see leaps and bounds and not itty-bitty steps, we're talking about infinity. Since this is heading towards Satan, negative infinity. This is heading upwards, so this is positive infinity. These infinities imply D and E, but heading to negative infinity. You don't have to write D and E, that's what it implies. Now, they're different infinities, so now my limit has to be D and E. I don't have an ordered pair. My function value is undefined. But when you have infinities, your answer for the discontinuity is infinite vertical asymptote, and as in college books will say, unbounded, including your textbook. So we approach zero from the left and from the right. Once again, notice leaps and bounds. Leaps and bounds. This side is getting larger and larger and larger, positive infinity. This one is going to hell in a handbasket, negative infinity. These are unequal, so the limit doesn't exist. There is a vertical. There is a point on the asymptote. There it is. But we have infinities. And so it's infinite vertical asymptote unbounded. Now, the little tour de France, so to speak, making it to the next room. Some more with these. Play with it a little more. I'm approaching -3 from below, from above, or the left side, the right side. Again, leaps and bounds, not itty-bitty steps. I've done powers of 10, but it can be powers of anything, folks. It's just you're not going by decimal points, but by multiples. And so I see this is heading towards Satan, and this is heading towards Satan. They're both negative infinity. D and E, but we write negative infinity. Since they're both negative infinity, the limit is called negative infinity. If you wrote it in writing, you would say, oh, the limit does not exist, but both sides are heading towards negative infinity. The function value doesn't exist, but we have infinities. So the answer is it's an infinite discontinuity. It's a vertical asymptote. It's unbounded. The last one that deals with infinite is we'll go from the left and from the left and from the right, or from below and from above. Notice leaps and bounds. This is itty-bitty, but this is leaps and bounds, leaps and bounds. And both of these are heading towards positive infinity. Since the infinities match, we say the limit is positive infinity. In writing, the limit does not exist, but the behavior is that it's going towards positive infinity. If you want to interpret, I have an ordered pair, it doesn't help. I have an infinite discontinuity, a vertical asymptote, unbounded. Now, the last one's difficult to demonstrate in a table, and this is oscillating. What we notice is that we're supposed to either be taking itty-bitty steps, itty-bitty, itty-bitty. We're not supposed to go this huge amount in between, because if this was getting closer, then these digits should be staying the same. The first two, they don't. Over here, getting closer, getting closer. This one, that was supposed to be a 9 there, and I wrote a 6. My apologies. Pretend like that's a 9. If I can get a marker here, I will do 9. And notice this one was actually getting a little bigger, and then all of a sudden it's jumped smaller. What's going on? And so this is how a table would look. You'd probably have more numbers in it for oscillating. We have one on your worksheet, and when you see a situation, D and E from the left, D and E from the right, the limit does not exist. The function value will never exist, and it's called oscillating. This will be seen on worksheets where we'll give you pictures, but on Limits 3, you'll actually get to type one into your calculator, and you'll get to see the cuteness that happens when that occurs.